Alright, my friends, here we go. Today we're going to talk about, yes, you guessed it, your favorite molecule and my favorite molecule, or maybe not, but at least an interesting molecule called hemoglobin, right? I started talking about this the other day because I wanted to shift from the immune system to the hematological system and the cardiovascular system and the blood, and I realized this is a level deeper than the blood itself, right? The description of how blood functions and plasma functions and whatnot. But I wanted to get into this because also I've always had an interest in hemoglobin for the reason that it's often mentioned as one of the model study molecule complexes in biochemistry. People have studied it a ton. It's also physiologically very important, and it seems like we know a lot more about hemoglobin. It's a case study in understanding molecular binding patterns and interesting behavior of molecular complex binding, and can be translated to perhaps other situations, the behavior of hemoglobin. So let's talk about it a little. So the other day I believe I talked about the structure of hemoglobin, how hemoglobin consists of 4 subunits, alpha 1, beta 1, alpha 2, beta 2 chains, and the beta subunits are equivalent in structure to the alpha subunits, but they're arranged where you have a beta subunit on top of an alpha subunit, and you have another beta subunit on top of an alpha subunit, and you kind of split these in half, right, in terms of dimeric components instead of 4 different polypeptide chains connected to each other. So you treat this hemoglobin as an alpha beta dimer. Okay, so we talked about the prosthetic group for hemoglobin called heme the other day, which is actually that's how oxygen binds to the hemoglobin molecule through this prosthetic group called protoporphyrin. Okay, so it's that this kind of like iron that's centered, and what you're seeing is kind of the transverse view of this molecule. So you kind of see it on its side, where the iron is in the center of the plane, and you see the plane of the protoporphyrin sideways instead of from the top. But basically what happens, again, I'll just quickly review, and this is important because this will get into our discussion about the T state and the R state, is that the oxygen binds to the iron atom, which has iron has a very high electron density, right? And so that's why you can think of it as kind of heavy, and thus it when it's not bound to the oxygen, the diatomic oxygen, it kind of pulls the plane. It sinks in the plane of the protoporphyrin molecule, which is holding it in place. So what has to happen is that when that iron sinks like that, remember, there is this distal histidine connected to it. Okay, actually, sorry, the proximal histidine connected to the iron, and that proximal histidine connects the iron to the rest of the hemoglobin molecule, right? And so this is connected in several places within the hemoglobin, but we don't have to go into that right now. All you have to know is that once the oxygen is loaded, then the electron density distributes between the iron atom and the oxygen, and then the plane becomes more straight, right? Like from the side, it's no longer bent. The conformation of the iron is no longer bent in the protoporphyrin, center of the protoporphyrin, and what this does is this causes the proximal histidine to pull up. Okay, so see, you can see it here. This proximal histidine, first it's bent. This is an upside down diagram, so but the proximal histidine is up here, and what happens is when the O2 binds, the proximal histidine flattens the plane, and this proximal histidine is connected to the alpha 1 helix in this case, right? So because that is the situation, the alpha 1 helix is itself pulled, and its structure changes somewhat. And because its structure changes, it kind of affects the entire hemoglobin macromolecular complex, and thus it goes into what's called the relaxed state. So the reason I'm bringing up the connection of the alpha helix to the proximal, to the proximal histidine is because that is important in how hemoglobin performs cooperative binding. It's actually really, really deep and interesting, right? Because in this T state, before the oxygen is loaded, T stands for tense, before the oxygen is loaded. And you would think it's interesting because it's tense, it looks tense because it looks like the iron atom is taut, right? But it actually has to do with this chains, right? So in this tense state, the heme groups are not as easily exposed to the O2 molecules, because the rest of the chain itself is in a structure that makes it harder for these heme groups the oxygen to access these heme groups. But what happens when an oxygen binds to one of the heme groups, essentially the entire hemoglobin macromolecular complex and all the subunits go into this R state or relaxed state, this oxyhemoglobin relaxed state. And because of this, the heme is more exposed to oxygen, and thus it can bind more easily. So once you've bound oxygen, then the continued binding of more oxygen to the rest of the heme sites becomes a lot easier. And that's called cooperative binding, because the more oxygen present, the more hemoglobin cooperatively binds the additional oxygen. And that kind of makes sense because because hemoglobin in the lungs, existing in the lungs, is the source of most of the oxygen transportation or oxygen capture of the bloodstream. So that's because your lungs is where your oxygen comes in. So right from there, you want to start transporting to the different tissues that need it, right? So here's something to understand. The myoglobin, by the way, does not have the same situation going on because it only has one subunit, and therefore it has a much higher oxygen affinity to that subunit. So regardless whether the oxygen is bound or not, it won't cause other adjacent myoglobins to change their affinity. It's only that the conformational change of this hemoglobin caused by an oxygen bound to this hemoglobin molecule molecular complex causes the affinity of the other hemoglobin to increase. Okay, so let's go to the oxygen binding curve, because I think this is important to talk about. So you have so this is interesting, right? Because what is exactly happening here? Like, does hemoglobin become more relaxed as more oxygen molecules bind, or does the oxygen molecule binding to the hemoglobin put it in the relaxed state, and as more and more hemoglobin bind to oxygen O2 bind to heme groups of other hemoglobin, do more relaxed state hemoglobins dominate tense state hemoglobins? So that's interesting, because in this situation, in nature, we don't really see either single behavior of R state binding. Like, let's say, like, one thing we want to look at is the R state binding curve of hemoglobin. If there was only molecules in an R state in hemoglobin, right, in the relaxed state, that means it would look like a traditional enzymatic binding of hemoglobin, in the same way that myoglobin binds enzymatically through the Michaelis-Menten model to oxygen, right? So it's a straight up enzymatic activity binding exponential curve, right? And so it would pull up hemoglobin real fast, but in the relaxed state, it would be hard for the hemoglobin to be letting go of oxygen easily. So, but in the T state binding curve, it's different. You have this like kind of slow, gradual increase in percent oxygen captured based on the pressure of oxygen present within the area where the hemoglobin is binding this oxygen through its heme group. And essentially what happens is that this is not, this is what would happen if you have all T-state molecular complexes, molecular hemoglobins. But since that's not the case, you don't have only T-state or R-state molecules. You presumably have a mix of both, right? So what happens is, this is not the right curve, but the sigmoidal curve is the actual correct curve. But we talked about it yesterday. This cooperative sigmoidal curve is the right that exists between the R-state and the T-state curve. By the way, this is apparently for other molecules, but this is the better one for hemoglobin. This has a similar, so this is basically a better curve because it doesn't put the wrong molecule on the left. But yeah, so this intermediate state is what actually we see in nature. Now, the interesting thing between the T and the R state, right, is that, you can look at the T state and the R state through this kind of diagram here, because here you can pretend each of these subunits is part of the hemoglobin alpha 1 and alpha 2 chains, right, 1 and 2. And what happens is that as oxygen binds, your affinity increases, and thus these conformational changes make it easier for more oxygen to bind. Okay, so you start with T state and then you work your way to R state, right? So now, what exactly is going on here? Because there's actually, if you look at, there's two models of binding, called the concerted model and the sequential model of binding. In the sequential model of binding, right, or the concerted model of binding, you have hemoglobin kind of, as oxygen binds to hemoglobin, these boxes are tense state and these circles are relaxed state. As oxygen binds to hemoglobin, sort of an equilibrium forms, where there's a shift between T and R state molecule complexes, right? So basically hemoglobin's either completely in R state or completely in T state, but the more oxygens that bind and the more R state present, the less T state is present, and so the equilibrium shifts such that the concentration of R and T state molecules eventually shifts, the balance of power, so to speak, shifts until the equilibrium exists almost 100% between the R state and the T state, where the R state is dominating the T state. But that is one model. That means there's no intermediate thing between T and R state. There's either molecules that exist in the T state or molecules that exist in the R state. So that's not necessarily true in the sense that there are intermediate states. Now, you see, in this case, there's either the R, all the circles connected together, or there's the T, which all the X's or all the boxes connected together. But the sequential model says, in order to account for the lack of accountability of behavior for the conservative model of hemoglobin binding, the sequential model shows you a mix of different binding states, right? So there's intermediate R and T states that occur. So basically, as oxygen gets more and more bound to the hemoglobin, the T state shifts more and more to be R-like until it's completely R, and there's the intermediate sort of semi-R states, right? Now, the issue with this is that neither of these models of bonding of hemoglobin is 100% correct. They apparently need to be accounted and work together to account for the actual behavior in nature, and I'm not sure why that is yet. That's probably been studied, but it's just something to note that you can't just rely on one model to kind of predict hemoglobin's behavior. You need to take into account both the sequential and the concerted models, and that applies to other enzymes as well, apparently. So last thing we want to note, what's really cool about the way the hemoglobin works, if I can get a good diagram, is that the reason that the chains, the alpha and beta chains, kind of work together is actually very complicated once they start folding together to form a better conformational structure for oxygen absorption. But essentially, the alpha 1 and beta 1 dimers are referred to as dimers separately because, even though there's 4 units, because once oxygen binds to the heme of one of the alpha groups of one dimer, the entire dimer rotates. So those two, the alpha 1 and beta 1, rotate, and the alpha 2 and beta 2 rotate together, and thus become both more conformationally adapted to taking in more dioxygen or molecular oxygen. So that was a mouthful of me kind of spitting out this info. You can call it, some people, you can call it regurgitation, whatever. I'm trying to present it in a certain way. But there's a lot of stuff here, and the next time I do this lecture, I'm going to break it down into several pieces. But yeah, this is just for today. So January 23rd, 2022. Like this video if you so found it useful, and subscribe. Okay, I'll see you later.